Anyway, I'll be the spokesperson for the team today. We'll talk about this water quality metric improvement project that we've run for about a year and a half. Actually, it's actually closer to a year. And the project was really structured around the idea that there were some improvements that were required right now to the metric, and there's a long-term process to aim for the best metric we can over a number of years. This first phase was really to try and address some of the pressing issues. And I think John's point about the fact that we don't know exactly what's happening out there is really the point about this project, is that it's sparsely observed. It's really hard to know what's exactly going on in there, and we try to integrate some monitoring and modeling approaches to try and get a better answer. But it's certainly not the be-all and end-all, at least in a year. The first phase was to address this for the report card that's just been published, and to also identify the long-term improvements or the research gaps that we think are required to be addressed to get to a metric that we would be satisfied with. Now, in terms of the perceived limitations of the existing metric, I mean, they've been discussed in the past, but essentially it was mostly uniquely based on remote sensing and extracting optical properties such as chlorophyll, ATSS, etc. from the signal you get from the true color images that we get from satellite. And that had some limitations, first of all in terms of the quality and the accuracy of the data in different areas, and especially in complex waters, shallow waters, but also the limitation associated with the fact that you have some cloud cover, so when you get no satellite data in these times. And there were some other limits, and one aspect that really concerned, in particular the ISP, but also other stakeholders, was the fact that the metric didn't seem to be replicating some of the properties we know of the reef. You know, the water quality gradients from north to south, and some behaviors when you get very large rainfall and flooding, and we didn't seem to see the correlation in this context. And that was not only due to the remote sensing, but also due to the way we were calculating the metrics. So this project was really about working these two aspects. And originally, the first concept was about bringing together more data. Can we bring more of the in-situ sampling data along with the remote sensing, loggers, models? Can we bring all that together into a better metric? The reality of it is that with a sparsely observed system, if you've got only a few sites where you've got in-situ sampling data, it's almost impossible to statistically bring that together into, as soon as you start averaging, you either lose the sparsely observed data or you give too much importance to that data. And the GBR system being so dynamic, it's very, very hard to combine all this. So the project looked at this data, tried to identify whether this data was fit for purpose, but also looked at the calculation methods and the aggregation methods to try and develop a methodology of scoring which is more appropriate. The other, I guess, line of work for this project was to look at whether we could use the ERIX model as an integrator of information, essentially. So bringing the remote sensing into the ERIX model by doing some data assimilation, and using the in-situ sampling data as the verification data for our model. Very quickly, we realized that we could not obviously aggregate this very different data over a large area. That was pretty obvious, but we confirmed that. But what we did was to look at some of this information and try to assess whether we could combine these or whether they were all carrying some relevant information. I guess the idea here was to say, is there a set of data that we can completely ignore because it doesn't have the qualities we need? And we looked at, so here's an example of what we did. There's a lot of detail in the report that will be published later this year, but we looked at marine monitoring sites, the black dots here, and we looked at the distribution of points from the remote sensing around that. So the grid is 1 kilometer wide. For each pixel, it's 1 kilometer square. For ERIF, the model that we used there was 4 kilometer by 4 kilometer. And what we're showing here is the match of data from one particular set of data to the marine monitoring sites. Obviously, the NMP sites were not designed to match the model grids. They were just there for other reasons. And when you start matching these, it can be quite challenging. An example here is the top right, where you actually see that there's only really one point here that you can really bring the ERIX data next to the marine monitoring site. But the one bottom right, you've got more data points that you can bring together and compare. So we tried to compare all these data sets and look at their behavior over years and see whether there was any data we can exclude or whether they should all be taken into account. I won't present that here because there's a lot of information, but essentially we didn't find any reason to exclude data. They all seem to provide some valuable information, and as I mentioned before, because we don't know what the truth is, we decided that the data that's there is still valuable. Now, there are some areas where you wouldn't rely on one particular data set. It's obvious from the time series, but generally, in different areas of the reef at different time periods, they provide relevant information. What we did then was to work on this data assimilation scheme with e-reefs. So essentially what we're trying to do here is to use the remote sensing data to ground the model further and to make sure that we're closer to what's actually happening in the environment. Now, I'm not going to explain that today, and I'm not sure that I can, but Mark is over there. I asked him last night over a glass of wine whether he could give me a 2-minute explanation I could give to you guys, and there's none. You need more than 2 minutes. You need to speak to him, and but I'll give it a go today. So essentially what we're trying to say here is we can use the e-reefs model to simulate what you would see from a satellite, essentially, because the model, you've seen a graph before, I think it was Katerina or another group, was showing the complexity of the model, but essentially it's able to simulate the optical properties of the water by modeling the different components. So you can recreate an image that you can then match against the satellite observations, and the true images from the satellites we're quite comfortable with. It's extracting the properties within the water that people and stakeholders were less confident about. So we can match the images of the satellite to the images of the same environment that the model would simulate. And what you do is you essentially create an ensemble of realities of the model. So you slightly perturb your model and create 100 different paths, and at some points in time, you compare that to what the satellite is telling you, and you adjust your solution to what the satellite is telling you. So you're not simply aligning your model to what you see from satellite. You're slightly perturbing the variables, and you're trying to find the path that is the most likely in this context, while retaining consistent simulation. You're not bending the properties of physics, you're staying within the environment of your model, but you're trying to match that to what you know of reality at that point in time. Now, that's what you could think of, and I think as I look at this, I'm probably going to avoid that completely. It's going to take me too long to go through it. But essentially, if you let your model running freely, it's going to go through its path, and that's the black line here. But what you want to do is to create this ensemble of solutions. And when you look at this, I'll try to avoid the fall here. But if you look at this, you've got the boundaries in dashed lines of what your ensemble is telling you. So all these different solutions have a variability, and they show you this spread of your ensemble. And the mean is the big dashed line here. And what you try and do is at some point in time, try and use the observations as blue stars to realign your mean as you go, and you rerun your solution. So you maintain within the realm of your model. You stay within the realm of your model, but you're actually adjusting the solution constantly. And as you get more observations, your spread gets narrower and narrower, and you're more and more confident about the solution. Anyway, doing this, we ended up with an improved solution for the model for the various parameters. And here we were talking chlorophyll A, NOx, TSS, and Secchi depth were the parameters we were looking at. What we did next in this project was to look at the different methods to calculate indices. There was a big flaw in the previous metric, I think, that the binary compliance approach that was used was probably removing a lot of the signal and the information that was in the data we had. So what we did was to look at a number of ways to calculate your indices. So what we mean by indices is, are we having good or not water quality from 0 to 1? How do you calculate that? And we used different methods, and we compared these. The one that we settled on is the modified amplitude method, which allows you to have significant sensitivity around the threshold, what you consider an important threshold, but also allows you to cover the entire spectrum and potentially cap that. So for example, if you know that you're not really interested in water any clearer than this because you know it's good, you can assign a value of 1 to that, it's perfect, it's fine. You don't need to get more sensitivity there. You're interested in the sensitivity of your metric within that space where you think that's affecting most your ecosystem. And the way we looked at that was statistically, we looked at different distributions of the data and how your different indices will respond, and you can start seeing some variation, especially when you get into the low data space. And not going into the detail here, that's in the report, but what you can see is that depending on the method, some will lose the linear sensitivity that you're after. i.e. you want to be able to cover the whole range and have your index responding to that whole range in a linear fashion, or as close to linear as possible. And here what you see is that the modified amplitude method responded quite well to the whole range of statistics for your data. But it was a different story for the exceedance or max duration or binary, which for smaller data sets starts getting really black and white. We also looked at aggregation methods, and that's particularly important when your data sets are of different size and different distributions. So we looked at different methods to do that, and that's been done in the past, so we simply applied that to the project. And then we looked at the hierarchy of integration. So where do you work? Do you start aggregating across space or time, across indicators, or across measures, or across indices? So there are a range of combinations you can have here. And what we landed with, which was the most obvious for us, was to work at the site level. What we call a site is a pixel in our case, because it's a model. And at the site level, we look at the measures that we have, and we do the aggregation into indicators or sub-indicators. What that might be things like Secchi depth and TSS being combined into a water clarity indicator or something like that. So there are a range of combinations you can make there to reach your result. Once you've done that, we can aggregate in time. We aggregate in time at this level, and then you can aggregate in zones. You can aggregate at the whole of GBR after that. One aspect that was really not contentious but difficult with this metric is what is the reference? What is a good water quality value? What is the right amount of chlorophyll? What is the right amount of TSS? And that's proved really difficult. What we did for this project, considering the time we had, was to go back to the guidelines. And we used the marine water quality guidelines as much as possible, and Carol was really helpful in helping us translate that. But we just worked from that as the basis of this metric. We all realized that it's an area that needs more work, but within the confine of the project, we couldn't look at that. But I heard today, we looked at the new indicators that are being developed, the light indicator with Katerina. We looked also now at combinations, nutrients, light, pesticides, temperature. All these things are accessible to a metric of this kind, but we need as a community to agree as to what is good and what is an appropriate index for this type of values. The other aspect that we looked at is what do we define as a reporting period. So in this case, we went conservatively with the idea that we're going to take the whole year from 1st of October to 30th of September. Historically, it's captured the rainy season. And when we started to look at approaches more complex about picking different starts for the wet season, it got really complex because different catchments will have different starts. And so we went back to a very simple 1st of October to 30th of September water year. And that's the summary of how report card, the metric for report card was generated this year. So October 1st to September 30th, we used the Reef's 4-kilometer resolution biogeochemical model using the assimilation of the satellite reflectance using the MODIS sensor. We used the in-situ river flow monitoring to feed the hydrodynamic model, and we used the source catchment concentration data as the best estimate of the contaminants coming down the river to feed the model. We used chlorophyll A and Secchi depth as our indicators, and I'll speak later as to why we didn't use TSS. And we used the fixed cap amplitude method, which I mentioned before, and that's something we are looking at still at the moment. The threshold values were based on the guidelines. Aggregation zones were standard, so the open coastal water body in the 6 NRM regions, and we used the uniform grading scale from A to E, which has been the practice to date. And that led us to a report card, and that's available. The main point, though, is I'll just take chlorophyll A. We're quite comfortable with chlorophyll A, and we got a lot of validation data, and we think the model is performing quite well. And when you look at these, the squares are the previous metric, and the circles are the new metric. So obviously, huge gap, and from a communication point of view, that's something that we're looking at in terms of being able to relate to that. But what we see here is that we see a much better gradient from north to south with the new metric. We also saw some reasonable improvement over the last few years. What we'd like to do now is go back in time and cover the years 2011, 2010, 11, 12, 13, because that will give us a better indication of how responsive the metric is to the water quality. But we know from the IRIS model that we capture that gradient as well quite well. Now, the future improvements, so as I mentioned before, that was really just the first go at it, and in fact the list of needed improvements is just getting bigger and bigger every day. So there's quite a bit of work to do, and we have some further funding within ERIFs, thanks to the federal government, to further that and to do some work on this metric even further. And we're working with the Australian government and the Queensland government to define exactly what it is we're trying to achieve through this process. But the first thing that I would mention here is the suspended solid modeling. We know there's a lot of work to do there, and Katerina, you mentioned the fact that there's a clear correlation between the high rainfall or high discharge from the catchment and water clarity. What we're starting to see more and more is that the model we have at the moment probably doesn't cover enough some of the complex classes of sediments, such as flocks and very, very fine sediments, to be able to correlate that or to predict that accurately. And so we are planning to do more work in this space to try and improve what the model is doing. At the moment, we know that it's a very complex scientific space, and that might be a limitation for us, but there might be ways around that to try and model what we know is happening already. And to show you an example of this is our metric at the moment, and it's a combination of our model's response, but also of the guidelines threshold where it is sitting at the moment. Our results are saying that it's great everywhere. I think that's probably not reflecting the picture properly, but it's a combination of things here, the guidelines and also the way we're modeling the suspended solids. We want to produce, and John mentioned that in this water quality target setting project, we need to represent the rivers coming into the reef better. We capture most of the discharge, but locally, when you start going at the regional level, it becomes really important whether you capture all the tributaries and how they get into that system in these estuaries and then into the coastal environment. The model can integrate 70 rivers. The problem we have is we don't have the hydrodynamic data, so we don't have the flow data for these rivers, and we don't have real-time concentrations, but we could use the source catchment data to get the concentration and use that in our model.